Welcome back. This video is going to be about Chapter 5. One of the things that we learn about in Chapter 5 is this concept known as a random variable. A random variable is a numeric value that's associated with each outcome in a probability experiment. In other words, when we do a probability experiment and we get the outcome of that experiment, if we count something or measure something in that outcome, then we have what's called a random variable. And we often use the letter X to represent that variable. Now, if we're counting something in the outcome of our probability experiment, then we'll say we have a discrete random variable. If we're measuring something, then we'll say that we have a continuous random variable. In Chapter 5, we focus primarily on discrete random variables, and we'll see continuous random variables in the future chapters. Just as an example of a discrete random variable, let's say that we were to take a random person and ask to see their phone log for the past 24 hours. If we count how many phone calls they have made in the last 24 hours, that would be a discrete random variable. We would be counting something. That's what makes it discrete. And one of the key features of a discrete random variable is if you were to plot the number, the outcomes for the random variable on a number line, you would get a set of distinct dots. So if we look at somebody's phone log for the past 24 hours and count how many phone calls they've made, it could be 0 phone calls, it could be 1, it could be 2, it could be 3, 4, 5, 6, and so on. You would just get these distinct dots on the number line. You can't have somebody who made 3.6 phone calls in the last 24 hours or 4.1 phone calls. It doesn't work that way. You just get 0, 1, 2, 3, 4, or 5. So you're counting, you're getting these distinct dots on the number line. By way of contrast, if we were to take that same phone log and look at how much time the person spent on the phone in the last 24 hours, then we would be measuring something. Time is something that we measure with a timer or with a stopwatch. And that person could have spent anything between 0 and 24 hours on the phone in the past day. So you would get this whole range of numbers on the number line. That's a distinct feature of continuous random variables. Now, like I said in Chapter 5, we're going to focus primarily on discrete random variables. And what we're ultimately going to be looking to do with that random variable is create what we call a discrete probability distribution. A discrete probability distribution is a table that will list each possible value that the random variable can take and the probability that it takes each of those values. So there'll either be 2 rows or 2 columns. One row lists all the possibilities for the random variable, and then the other row or the other column would list the probability that you actually get those values. Now, 2 rules that discrete probability distributions always follow are these. If, first of all, the probability of getting any particular value for the random variable has to be a number between 0 and 1 because it's a probability. Also, if you add up the probability of getting all the different values of x, that total must always be 1. Okay, let's look at a probability experiment where we flip 3 coins. And let's say that we want to count how many coins land on heads. That would make our random variable a discrete random variable. We're counting something in the outcome of our experiment. Now, in order to come up with a discrete probability distribution for this random variable, the first thing that we'll need to do is come up with the sample space. Now, since there's 3 coins involved here, it might be best if we used a tree diagram to come up with our sample space. So think of a penny, a nickel, and a dime. The penny could be heads or tails. So I start with 2 branches. If the penny is heads, the nickel could be heads or tails. If the penny is tails, the nickel could also be heads or tails. So 2 branches coming out of each of those. And then no matter which way the penny and the nickel land, the dime could always be heads or tails. So if you got heads, penny, heads, nickel, you could get heads or tails on the dime. If you got heads, penny, tails, nickel, you could get heads or tails on the dime, and so forth. So you can then trace the tree from beginning to end, like we learned how to do in Chapter 4. You can come up with this sample space where you've got 8 different outcomes when you flip 3 coins. Now, for each outcome in the sample space, what we want to do is figure out what would the value of the random variable be. So if all 3 coins land on heads and you're counting the number of coins that land on heads, you would count 1, 2, 3, and you would say X is equal to 3. If you get heads, penny, heads, nickel, tails, dime, and you wanted to count how many coins landed on heads, you would count 1, 2, and say X is equal to 2. HTH would be 2. HTT, that's only 1 coin that landed on heads. You can go on down the list. The last one, where all coins are tails, you would have 0 coins that landed on heads. Now, once you've figured out the value of the random variable for each outcome in the sample space, the next thing that you can do is you can begin to draw your table. And I'm going to draw this table with 2 rows. On the top row, I'm going to list all the different values that the variable could take. So I just look at this list, I see 0, 1, 2, 3. Those are the different numbers I see in the list. So I just go ahead and put those on the top row, 0, 1, 2, and 3. Now for the probabilities, what I do is I say, okay, how many of the outcomes will make X equal to 0? Well, there's 1 out of the 8 that makes X equal to 0. How many make X equal to 1? We've got 1, 2, 3 outcomes that made X equal to 1, so 3 out of 8. Okay, this is just classical probability analysis. How many outcomes make X equal to 2? 1, 2, 3 outcomes out of 8. And how many make X equal to 3? Well, just 1 out of 8. If you add these probabilities up, 1 plus 3 plus 3 plus 1, you would get 8 out of 8. So the distribution meets the rule that I said it has to follow. And you could also put these probabilities as decimals if you wanted to, even as percentages. Now you can also take this probability distribution and express it as a graph. There's really 2 different ways that you can do this. One way is you just draw your horizontal and vertical axis, and you mark down the values of X on the horizontal axis, probabilities on the vertical, and then you just draw these sticks for each value of X, where the height of the stick corresponds to the probability. You might also see people draw rectangles that straddle the values of X instead of the sticks. It's just a matter of preference. It's the same information, just presented 2 different ways. Okay, now once we have our discrete probability distribution, we can describe various features of it. And so one of the things that we can do with our discrete random variable is we can describe the center of it by calculating its mean. Now, the mean of a discrete probability distribution can be found with this formula. It's the sum of each value of X times its probability. So let's take a look at that distribution that we just came up with, where we flipped 3 coins and counted the number of heads. So here was the distribution that we came up with. Now, whenever I'm calculating the mean of a distribution, I usually like to put the table in vertical form, and I like to express the probabilities as decimals. So here's the first column with 0, 1, 2, and 3 for X. In the second column, I've got the probabilities in decimal form. 1 divided by 8 is 0.125. 3 divided by 8 is 0.375. And so I've got the probabilities there in decimal form. Now, to work out the mean of this distribution, what I do is I just take each value of X times its probability. So 0 times 0.125 is 0. 1 times 0.375 is 0.375. 2 times 0.375 is 0.750. 3 times 0.125 is 0.375. And then I just add that column up, that last column, and that would be the mean of my distribution. So 1.5. And one way that you can think about that 1.5 is you can think about that as what you would expect for a long-term average. If you did this experiment, let's say every day for a year, you woke up, you flipped 3 coins, wrote down how many landed on heads. So at the end of the year, you would have 365 results in your notebook. Some would be 0, some 1, some 2, some 3. If you averaged all those numbers out, added them up, divided by 365, you would expect your result to be about 1.5. So it's like a long-term average. Really, this mean of a distribution calculation, it's really just a weighted mean calculation where you're averaging these values of X and the probabilities are serving as the weights. So if you remember our weighted mean formula from chapter 3, we're really just applying it here where the values of X are 0, 1, 2, and 3. The probabilities are the weights. take each value of x times its weight, add those up, and then if we divided by the total amount of weight, since the total of the probabilities is 1, we would still get the 1.5. So it's really just a weighted mean calculation. Okay, so we could talk about the mean of the distribution. We could also talk about variance and standard deviation. So if you want to calculate the variance of a discrete probability distribution, here's the formula. So you're going to take the summation, remember our summation sign, it's going to be x squared times p of x. Now once you've got that summation, then you have to subtract the mean squared. Okay, so let me show you how you can work this formula out. So the first three columns are what we've already had when we calculated the mean, the values of x, the probabilities, and then each value of x times the probability. Now I'm just going to add two more columns on. I'm going to add an x squared column where I take 0 squared and get 0, 1 squared and get 1, 2 squared and get 4, 3 squared and get 9. Then I'm going to take each value of x squared times the probability. So 0 times 0.125 gives me 0. 1 times 0.375 gives me 0.375. 4 times 0.375 gives me 1.5. 9 times 0.125 gives me 1.125. Now I add that last column up, that gives me 3. So that would be the summation part of this variance formula. Now we have to take that 3 and subtract the mean squared. So 3 minus 1.5 squared. Well, once you work it out, you should get 0.75, or if you round it to one decimal place, you would get 0.8. Standard deviation, that's always the square root of the variance. So square root of 0.75 would be 0.866, or if you round it to one decimal place, that would be 0.9. So we can describe the mean, the variance, the standard deviation of this discrete probability distribution. The mean tells us something about the center of it. The standard deviation tells us something about how spread out those values of x are in that distribution. Now, sometimes whenever our probability experiment is one that involves money or gambling of any sort, we can talk about the expected value of the raffle or the game, whatever it might be. The expected value is just another name for the mean of the probability distribution. It's just that we typically use this terminology whenever money's involved with the probability experiment. So for example, let's say that we have a raffle where we sell 1,000 tickets for $1 each. One ticket's going to be drawn out for a $500 prize. We might want to calculate the expected value of a ticket in this game. Well, to calculate the expected value, what you should do is you should list out the different possibilities when you play this game. Well, you could either win or you could lose. The random variable when you're calculating expected value is profit, which is how much you win minus how much it cost you to play the game. So if you win the raffle, you get a $500 prize, but remember it cost you $1 to play, so 500 minus 1 is $4.99 for your profit. If you lose, you win 0, but you still paid $1 to play, so at the end of the day, you're $1 short of what you started with, so your profit is -1. Now there's 1,000 tickets, one of them gets drawn to be a winner, so 1 out of 1,000 is your probability of winning, for 0.001 in decimal form. That means the other 999 tickets are losers. So 999 out of 1,000 will be losers, or 0.999 in decimal form. Now the expected value would just be the mean of this distribution, so just multiply the 499 times the 0.001, get 0.499. Take the -1 times 0.999, get -0.999. Add these up, you get -50 cents. So again, your long-term average, if you played this raffle every day, you could expect in the long run to be losing about 50 cents per day. You won't lose 50 cents on any given day. Some days you'll win, some days you'll lose $1, but in the long run, you can expect to lose an average of 50 cents per day. Now, if there's multiple prizes in the raffle, things don't really change all that much. Here's a raffle where 2,000 tickets are sold for $5 each. Let's say there's two $1,000 prizes, five $400 prizes, 10 $50 prizes. So if I'm going to create the distribution and calculate the expected value here, I start off by thinking of all the different scenarios. Maybe I win the $1,000 prize, in which case my profit would be $995, since it cost me $5 to play this game. 1,000 minus 5 is $995. I could win a $400 prize, so that would be $395 on the profit. 400 minus 5 is $395. If I win a $50 prize, 50 minus 5 is a $45 profit, or I might lose. Okay, you could always lose the raffle, in which case you win 0, and you lose the $5 that you paid to play, so -5. Now, in this case, there's 2,000 tickets. 2 of them will be worth a $1,000 prize, so a 2 out of 2,000 chance that you would win the $995 profit. There's 5 $400 prizes, so there's a 5 out of 2,000 chance that you end up with a $395 profit. There's 10 $50 prizes, so 10 out of 2,000 chance that you get a $45 profit. Now, altogether, that's 17 prizes. 2 plus 5 plus 10 is 17. So out of the 2,000 tickets, 17 are winners. All the rest are losers. Well, 2,000 minus 17 is 1983. So that's 1,983 out of 2,000 as losers. So you can convert those probabilities to decimals, multiply each value of x times the probability to fill in this last column, add those numbers up, you get -2.75 as your expected value. Now, when we did this analysis, we just assumed that a person could win one prize. Turns out, if you were to do the same raffle and allow a person to win multiple prizes, in other words, you take the winning ticket out, give them the prize, put their ticket back in, then pick the next prize, it turns out that the expected value is exactly the same. The analysis would be a lot more complex because now you have to think of all the different combinations of prizes that a person could win. But at the end of the day, it really doesn't make a difference because the expected value turns out the same. Okay, so those are some things that are in Chapter 5. In our next video, we will move on to Chapter 6.